Hello everyone. In this video, we will see what is relation and some important types of relations. So before moving to our main subject, so let me define few terms that will be useful in our discussion. I hope everyone knew these concepts, but again, I am paying the formalities. So assume we have two sets. Let A and B be two non-empty sets. Non-empty sets. Then what are the things that can be do with these two sets? So of course we can form a Cartesian product of these two sets. And to define a relation, we require Cartesian product. That's why I am saying this. So keeping in mind that everyone know the Cartesian product of two sets, and Cartesian product is a set of ordered pairs where first and second components are coming from first and second set respectively. So because A and B are non-empty, so Cartesian product is also a non-empty set. Okay, so this is a non-empty set. And if we have any given set, the one natural thing that we can do with that set is we can form subsets of that set. Okay, and if we collect all the subsets of a given set, then that collection will again form a set, and that collection will be called the power set of a given set. Okay, so what I have said is this: if X be any set, so let me start like this. Let X be any set, then what do we mean by power set of X? Power set of X means it is the collection of all Y such that Y is the subset of X. This is the only thing that we require in the definition of power set. Of course, if X is a finite set, then power set of X has a very beautiful formula for representing the numbers of elements in the power set of X. So note is this: if cardinality of X equal to n, then cardinality of power set of X, cardinality means the number of elements in the set, is is this number 2 raised to n. Okay, so this is the concept of power set, and power set is the collection of all the subsets of a given set. Okay, so we knew the concept of subset, but I want to define it for you. Suppose let S and T be two sets, then S is said to be the subset of T if this condition is satisfied. If for each S belongs to capital S belongs to T also. It means if each member of capital S is also the member of capital T, then S is known as subset of T, and T is known as the superset of S. Okay, so these kind of terminologies useful, and two sets are equal if both are subsets of each other. Okay, so keeping these points in mind, I am going to define a relation. So we have already defined the Cartesian product. This is known as Cartesian product. So let me write it. A and B. Okay, so this is the Cartesian product. So I am going to define a relation. Okay, but before moving to relation, I want to ask a question about Cartesian product of A cross B. See, B started with A and B, and then we form A cross B. That is a set. This is a set, and because this is a set, so we can find subsets. Of course, we can find subsets of A cross B because A cross B is itself a set. And if we collect all the subsets of A cross B, then that will be a power set of A cross B. So see, denote the power set of A cross B by this symbol. Okay, so this is the collection of all the subsets A cross B. Okay, in particular, if we have finite number of elements in set A and set B, then obviously Cartesian product also have finite number of elements. Okay, and in this case, the number of elements in the power set of A cross B is also finite. Okay, so let cardinality of A equals to n and cardinality of B equals to m. Then cardinality of A cross B will be n into m, nm. So A cross B is a set which has n is to m elements, and now we have formed a power set of A cross B, and we already knew if a set has finite number of elements, then power set has 2 raised to those many number of elements. Okay, so from here we can conclude that cardinality of power set of A cross B equals to 2 raised to n into m. So let me put a dot in between n and m so that it will be understood that it is product of two numbers. Okay, so these many subsets are there in power set of A cross B. Means power set of A cross B has 2 raised to n into m elements. And I am claiming bigger thing here. I am saying that each element inside the power set of A cross B represents a relation. Actually, this is the definition of relation. The definition of relation. From where to where? Relation means from where to where. We require at least two entities to to define a relation between those entities. Okay. If the entities are not same, then we have to replicate the same entity. Okay. So we require two things. So if you want to define a relation, first you go somewhere and bring two items. Okay. Then you can talk about relation. Otherwise, it will be meaningless. So I have A and B, two non-empty sets. I form a Cartesian product, and then I form a collection of all the subsets of that Cartesian product. Now I am showing that each and every element of that power set of Cartesian product will represent a relation. And actually this defines the definition of relation. So I'm writing the relation definition. A relation from, so let me write, because see, subsets are sets and subsets have nomenclature already. Their names are written in capital letters of English alphabet. Okay, so because I have said that a relation from some set A to some set B is a subset of A cross B, and we know subset is named by some capital letter of English alphabet. So I am also giving the name to that relation because relation is a subset. Okay, it will come in the definition. So let me write it, a relation R. A relation R from set A to set B is a subset of A cross B and vice versa. It means if, if you have a subset of A cross B, then it will be a relation from A to B. And if R is a relation from A to B, then it will be a subset of A cross B. In mathematical language, it is saying this. R is the subset of A cross B, or R belongs to power set of A cross B. I think this is clear. So this is the definition of relation. And, and every subset of A cross B represents a relation. The question is, how many relation does from A to B will exist? Question is, if you have a set A and here is set B, and you have something that you are seeing a relation R from A to V. So you are doing nothing, only you are taking a point A from here and taking a point V from here, and under this relation is nothing but it will be some rule. Under some rule, these elements will be connected, and that rule may be explicitly defined, may not be defined. It is not the matter here. And collect all such pairs, and you will say that that collection is a relation. Okay. The question is, how many relations are possible from A to B? And the answer will be number of relations will be as many as the number of elements in the Cartesian product of A and B. This means number of relations will be equal to number of elements in the power set of A. So total number of relations from A to B is same as cardinality of power set of A cross B, provided that A and B both are finite sets. If any one of them is infinite, then Cartesian product will be infinite. And there are infinitely many subsets of the Cartesian products. So there will be infinitely many relations from A to B. So this result holds if number of elements in each individual sets is finite. So in this say we can say the inequality, because infinite sets in infinite cardinal numbers may be equal, may not be equal. So there are various theories. Okay, so I'm not going to that. So till now we have discussed the concept of relation. Actually, what is relation? That we have discussed. And I want to give few examples to clarify this concept. So the first example, the very easy example. Take take A equals to natural numbers up to 10 and B equals to set of prime numbers. Let S is a new set that I am defining it. Question is S a relation from A to B? Question is this. Is S a relation from A to B? Is S a relation from B to A? So this is a question for you guys. Okay, और ये इजी प्रॉब्लम है, बहुत डिफिकल्ट नहीं है. Okay, I am doing second part. First part for you and second part I am doing it. In order to S be relation from B to A, it must be subset of B cross A. Okay, and because in the definition, अच्छा, you first think if S is a relation from B to A, then the first component of the trade pair will come from B and second one will be from A. Is it clear from the definition S that first component is coming from B? Think. From the definition, it is not clear. If you observe carefully, it is not clear. And it is even it is clear if I see. Because he is saying that A is coming from capital A and B is coming from capital B. But still we need to observe it. How to observe? So you first form the set S explicitly. So tell me few elements in S. So is one is related is 1 from capital A is related to some element in B somehow with that given relation A plus B equal to 10? The answer is no, because 1 plus 9 equal to 10, na? And 9 is not the member of B. The same question. Is 2 related to B? No. Is 3 related to capital V? Yes. The first member is 3 comma 7. What is the is 4? No. 5? Of course 5 is related. 6? No. 7? Yes. 8? No. And 9? Of course 9 related. No, sorry, 9 is not related and 10 is also not related. So, so we have only 3 members coming in the set S. So now you guess something. Is the first component is coming from A? Yes, answer is yes. Is the second component is coming from B? Answer is yes. Is the first component is coming from B? Answer is yes, coming. So from here you can easily see that S is the relation from A to B and S is also a relation from B to A. So it is a relation in both ways. This is the first question that we discuss was easy one. ये दोनों तरफ से रिलेशन था. So let us talk some different types of relation. Okay, of course, empty set is the subset of every set. So in particular, it will be a subset of Cartesian product of two sets. So backwardsly, it is a relation, and that is called empty relation or void relation. And we are not interested much in such kind of stupid relations. Okay, and another relation is also obvious. And what is that? The Cartesian product itself, because every set is the subset of itself. In particular, Cartesian product A cross B will be a subset of itself, A cross B. So A cross B will be representing a relation from A to B. Okay, so we have got two relations without any difficulty, and those relations are empty relation and the whole Cartesian product. Okay, and all other relations are needed to be examined and to find. So we require some extra work to find those relations other than these two. Okay, so let let us move ourselves in finding the various types of relations that are really important. And what are those types? Okay, मेरे हाथों में काफी पसीना है, so I'm not able to write properly. Let me clean it. So types of relation. Oh, I am writing relations. Types of relation is enough. Identity. Identity is very important subject in algebra. Here is also important. The first relation is identity relation. So before moving to this topic, let me say something that is useful for us. This concept. a relation on the set A. What do you mean by a relation on a set A? In the beginning, I told we require at least two entities to define a relation from somewhere to somewhere else. And it is asking a very mad question, a relation on set A. So this is the right time to talk such kind of things. A relation on the set A means a relation from set A to set A itself. So you have to replicate that set A twice. So take a photocopy of A and keep that photocopy in place of capital B, what you have learned earlier in the beginning, and now apply every concept that we have discussed till now. You will get the answer. And that terminology is especially known by a relation on the set A. I'm not saying from A to A. It is enough to say on A. It is clear that it is saying from A to A. Okay. So this is the meaning. A relation on set A means from A to A. Okay. A relation on the set A means from A to A. Okay. I R, that is the subset of A cross A, then R is a relation. So how many relations on set A? So if cardinality of A is finite, then total numbers of total number of relations on A equals to 2 raised to cardinality of A cross A, that is equals to 2 raised to n square. So why n square? Cardinality of A square. This. So these many relations are possible on set A. And now I am classifying relations that are coming from these 2 raised to cardinality of A square relations. Okay, this means I'm going to classify in my intro in this discussion. We will be classifying relations coming from this set. Okay, so please do not get confused from A cross B. The first example, of course, the identity relation. First example, identity relation. So in this discussion, we will take A be a non-empty set. So let A be non-empty set and R be the subset of A cross B. It means R is a relation from A cross A. These two are not different, they are the same as. So the definition is this. Why I am writing the definition? Let us clear it first. Then we can write easily. So you have set A. This is set A, and you have bunch of points inside set A, and you want to form a relation from A to A. So again A to A. So there are lots of again same number of points, same points actually. Now we want to find a relation on A. So what is that relation that you want to form? So you pick some element from here, suppose that is A, and pick the same element here, that is again A, and form the ordered pair. Collect such kind of elements in a set. And of course, A is coming from capital A. So this is also coming from capital A. So this set is known as identity relation. Are you getting my point? Now you collect all the ordered pairs, all those ordered pairs in which every element of capital A is appearing in the ordered pair with second component सेम. जो पहला कंपोनेंट है वही हमको सेम लेना है, बट हमको ऐसे लेना है कि कैपिटल ए का कोई भी मेंबर छूटे ना, हर एक मेंबर आना चाहिए और सिर्फ यही आने चाहिए. नो अदर ordered pair should come other than these. Then such subset of Cartesian product A cross B is known as identity relation. The definition is, it means if every element of A, if every element of capital A is related to A itself only, कैपिटल ए का हर एक एलिमेंट स्वयं से रिलेटेड हो ओनली, then we will say that relation is identity relation. Otherwise it is not identity relation. This definition: a relation R on A is said to be identity if A comma A belongs to capital R or A belongs to capital A only. Alternatively, R is this: A cross A and A belongs to capital A, or A related to A only for all A belongs to R. For all A belongs to capital A. This is the definition for identity relation. The question is how many identity relations are there on any given set? How many identity relations are there on a given set? Are they finite in number? Are they infinite in number? Or anything may be happen. It depends on set, or nothing can be concluded. What is your guess? And the answer is there is only one relation, that is identity. इस दुनिया में for each given set there exists only one identity relation. Okay, so there is no choice of finite, infinite, and other choices are also not available. So another important relation is reflexive relation. So let me talk about some examples now. Let capital A equal to set of prime numbers and define a relation R on A comma B such that GCD of A comma B is not equal to 1. So I am also doing wrong things. Where A and B both are coming from capital A. Check what kind of relation is this. First check whether R is a relation on A or not. If R is a relation, then check what about the identity relation. Is it or not? So before moving to the question, you first mention few elements in R. You find out few elements in R. What they are, how they look like. What is the specialty about A, and use that specialty in set R to find the members in it. Then other things are easy. So I am leaving this example for you guys. Now I am moving to a next type, that is reflexive. अच्छा ये जो वीडियो है किनके लिए यूजफुल है ये? फ्रॉम क्लास 11th ऑनवर्ड किसी भी क्लास का किसी भी एज ग्रुप का इंसान इसको देख सकता है. इसकी कोई लिमिट नहीं है और इसकी लिमिट अभी नहीं, जब और कुछ चीजें मैं इसमें एक्सप्लेन कर दूंगा तब क्लियर होगी. अभी तो ये बहुत बेसिक चीजें चल रही हैं. व्हाट डू यू मीन बाय रिफ्लेक्सिव? सो हियर आई हैव मेंशन identity relation, so I think I should give a very beautiful name, so I am giving it name capital I. It will be very nice to write it. Okay, reflexive relation. A relation capital R on A is said to be reflexive if This identity relation is contained inside the relation R. And I am again warning you, please, please do not confuse the term relation from something else. Relation is nothing but it is a subset of Cartesian product. R is a subset, capital I is a subset, and both are the subsets of A cross A. Okay. So in particular, I and R may also be the subset of one another. There might be possibilities. Okay. So if this possibility likely to happen, if this is going to happen, then this is known as ident reflexive relation. This is the only definition we require. So in R, at least we require elements from capital I. Okay. So to make any relation reflexive, you just introduce all the elements from identity relation, then that relation will be reflexive. But if you've got one member from capital I that is not inside R, even though R is huge enough, या यूं कहें everything A cross A except some one or more elements, then even in that case, that relation might not going to be a reflexive relation. Okay. So example. Also check whether I is a reflexive or not. Oh, this I. This in this example, the relation R that I have defined, is it reflexive or not? You have to check this. I am writing a remark here. Note, since I is a subset of itself, okay, it means I contains a copy of capital I. Hence, I is a reflexive relation. So during discussion of identity relation, I asked a question: how many identity relations are possible on a given set? And we got an affirmative answer with exactly one. If I ask same question here, what will be your answer? Suppose you have given a set A and I am asking a question, how many reflexive relations you can find on A? Are they finite, infinite? Nothing can be said. What will be your answer? Sorry. So these questions are of course not very difficult, but these question offers some kind of discussion. So you spend some time on these questions, experiment with few sets, then you will realize and then can conjecture some answer, but it is not as immediate as you are thinking. So of course in this case single reflexive relation is not possible. There might be more reflexive because I have already said I identity relation is reflexive. So one relation is reflexive, and you add something in identity relation, it will also be a reflexive relation. So you keep adding members from Cartesian product in capital I, you will get new reflexive relations. And if you keep doing this, you will get huge number of reflexive relations. So of course that number is not in our control. So it totally depends on the size of set with which you begin. Okay. So I have said lots of things, and repeatedly I am saying them. Might be that lecture will be boring for you, but sorry मैं इसे अच्छा नहीं पढ़ा सकता. Sorry, I can do this. पढ़ा सकता हूँ. So reflexive is over. We will come once we finish the types of relation. We will come in counting portion. Okay, we will count every relation. If sets are finite, then how many such kind of relations will exist? We will ask the question and then we will answer to that. Okay, and we have very nice formulas there. So no need to worry about things, but you pause the video and you conjecture a few formulas from your own. Okay, so reflexive is over. From here, I told one note, and what is another note? Capital A cross A, since capital I is contained in capital A cross A, hence A cross A is a reflexive relation. So I have told two relations that are reflexive. One identity and another is the universal set A cross B, A cross A, sorry. So moving to the third relation, what do you mean by irreflexive relation? Irreflexive relation. What do you mean by irreflexive relation? So from name, it appears that it is the negation of reflexive relation. A relation that is not reflexive is called a reflexive relation. But this is not the case. So this is not the absolute negation of reflexive relation. It is something different, but not completely different. So what was the reflexive relation? Reflexive relation क्या था? A reflexive relation was this. I was contained inside the R. Okay. And what do you mean irreflexive relation? In the definition of reflexive relation, I have taken this And for irreflexive relation, take this. A relation R is said to be irreflexive if I intersection are equal to empty. This is the definition. So let me write it. A relation R on the set A is reflexive if I intersection R equals to empty set. Then it is a reflexive relation. This is the only definition. The question is how many reflexive relations are possible. So we will answer these questions in the last. So now I'm moving to the symmetric relation. A relation R on the set A is symmetric if whenever A comma B belongs to R implies B comma A also belongs to R. इसका मतलब अगर हम ऑर्डर्ड पेयर्स के कंपोनेंट्स को इंटरचेंज कर दें तो आफ्टर इंटरचेंजिंग द ऑर्डर्ड पेयर components of ordered pairs, the new ordered pair will also should lie inside that relation. If this happens for each and every ordered pair, then such kind of relation is known as symmetric relation. We have discussed three kind of relations: one identity, one reflexive, and third one is irreflexive. Out of these three, which one is certainly a symmetric relation? This is the question. Okay, so this question is for you. Out of those three, which one will be the symmetric relation? So I'm writing an example. Suppose that your capital A will be a set of natural numbers and define a relation R like this: A comma B such that A plus B equal to even number. And this is a symmetric relation, and I am asking you to prove this. Okay, I am not asking you, I am proving this. Then R is symmetric, and what is the proof? Let A comma B belongs to R, then imply what does it mean? If A comma B belongs to R, then what is the required definition satisfied by that ordered pair means that A plus B is even. And if A plus B is even, what about B plus A? That is also the same number. And what this means? B comma is also member of R. So you started with you started with A comma B and you ended with B comma A belongs to R. And you started with an arbitrary element of capital R. And you have said that on interchanging the components of that ordered pair, it also be the member of capital R. This tells that R is indeed a symmetric relation. Okay, so this is a very easy example. You can try some difficult ones. But in my mind, right now, I can manufacture this example right now. But if I manufacture different difficult example, it will take time to prove that one, and I'm not much interested in doing those difficult problems because this is an introductory video where I want to emphasize on these definitions and early concepts regarding these. So I'm not much worried about those. In the similar line, what do you mean by asymmetric relation? Because I have told irreflexive relation, then I can also ask asymmetric relation. So asymmetric relation. Again, this is not a negation of symmetric relation. This is not, okay. Of course, this is a negation, but this is not a absolute negation. Negation is something different. In this case, reflexive. What is the negation of reflexive? A relation is not reflexive means what? Now you find one ordered pair in which both the components are equal, and that ordered pair is not a member of R. Then that relation will be not a reflexive relation. This is the negation of reflexive. But in irreflexive, R need not have any such element in which ordered pairs are equal. For not being a reflexive, we require only at least one. But for not being, but for being irreflexive relation, we do not require any of the ordered pair in which both the components are equal. Okay, so this is the huge difference between negation and absolute negation. Sorry, absolute negation and negation, they are like of course same. So asymmetric relation, I'm saying this is not a negation, absolute negation of symmetric relation. But of course, this is a negation, some kind of negation, because asymmetric relation cannot be symmetric relation. But in such kind of situations, one thing you can observe, जिन चीजों के कारण ये हो रहा है, सिमेट्रिक रिलेशन जिन चीजों के कारण हो रहा है, उन सारी चीजों को अगर आप एक्सपेल कर दें अपने उस ग्रुप से, तो जो बचेगा दैट इज नोन एज असिमेट्रिक रिलेशन. हमने इरिफ्लेक्सिव रिलेशन में ये किया, रिफ्लेक्सिव क्यों हो रहा था? बिकॉज वहां आइडेंटिटी अंदर आ रहा था, आइडेंटिटी रिलेशन अंदर आ रहा था. हमने क्या किया, पूरी आइडेंटिटी को निकाल करके बाहर फेंक दिया. इसको बाहर निकालने का मतलब क्या हो गया कि उस रिलेशन का आई के साथ इंटरसेक्शन एम्प्टी आ रहा है, तो ऑटोमेटिकली वो रिलेशन क्या बन गया, इरिफ्लेक्सिव बन गया. इन द सिमिलर वेन आई वांट टू डू asymmetric relation also. So you expel all those members from a symmetric relation due to which it is going to be symmetric. And how it is going? If some member belongs to R, then that ordered pair should also belongs to R. तो आप क्या कहना चाह रहे हो कि अगर कोई मेंबर आर को बिलोंग कर रहा है तो उसके इंटरचेंज करने के बाद ऑर्डर्ड कंपोनेंट्स को इंटरचेंज करने के बाद वो ऑर्डर्ड पेयर आर के अंदर नहीं आना चाहिए, और किसी के लिए भी नहीं आना चाहिए। भाई अगर कोई रिलेशन सिमेट्रिक नहीं है, इसका मतलब क्या हो गया, निगेशन हो गया ये सिमेट्रिक का। इफ सम रिलेशन इज नॉट सिमेट्रिक, इट मीन्स देयर एग्जिस्ट some a comma b belongs to R, but b comma a does not belongs to R. This is the negation of symmetric relation. अगर ऐसा हो जा रहा है, if there exists at least one such member in R such that this does not happen या this happens, तो वो हो जाएगा not a symmetric relation. But not a symmetric relation and asymmetric relation, these two concepts are different, extreme different. Okay, so I'm writing the definition. A relation R on the set A is said to be a symmetric relation if A comma B belongs to R, but B comma A does not belongs to R. And here include for all. This should hold for all. So this is a symmetric relation. So my question is a symmetric relation is identity relation, or a symmetric relation is an irreflexive relation? A very beautiful question suddenly came in my mind. Is every asymmetric relation is irreflexive? This is the question. Okay. Hmm. So the next relation. Again, question is how many asymmetric relations are possible? The sixth example is transitive relation. And this is the very nice relation. So in this case, we require lots of attraction. A relation capital R on the set A is said to be transitive relation if for each pairs of ordered pairs A comma C belongs to R also. Then that relation is known as a transitive relation. So we have discussed reflexive relation, symmetric relation, transitive relation. And if we combine these three relations together, then that relation will be called equivalence relation. And equivalence relations are very important because they partition the set. And partitioning of a set is very important concept in algebraic structures. If there is some algebraic structure and there is a relation defined on it, and if that relation is going to be an equivalence relation, then it will be a very beautiful thing. You will get lots of uh, nice known results you can apply there. So theory becomes more rich when you have a very nice relations on that's it. So I am defining what do you mean by an equivalence relation. Equivalence relation. A relation R on a set capital A is said to be an equivalence relation if it is reflexive, transitive, sorry, I should mention it first, symmetric, and transitive. If this, if these three things are satisfied for a given relation R, then that relation R is known as an equivalence relation. So first, we will see the technique of counting. So using counting techniques, we will count all those relations. Okay, counting of discussed relations. So first, okay, so let me form an array Okay, so this is an array of numbers. So suppose you start with some set A with finite number of elements. Suppose this set has n elements, A1, A2 up to an elements. Then how many elements are there in Cartesian product? A cross A will have members of this kind, AI, comma AJ, where AI, AJ, they belongs to A. Okay. So cardinality of A cross A will be how much? N square. Of course, cardinality of A equal to N. So A cross A has N square many elements. So now set these elements in this array. So we are playing a game actually. Okay. So this is an array. How many horizontal and vertical lines are there? One, two, dot 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 dot. So this is suppose N. One, two, dot 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 dot. This is nth number. So these are n rows. So here is A1, A1, यहाँ जो एंट्री आ रही है वो आ रही है A1 कामा A1, यहाँ आ रही है अच्छा why I'm taking order here A1 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 A2 A1 A3 ऐसे चलता है और ये आ गया A1 AN उसी तरह से दे क्या है A2 A1 A2 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 A3 A2 AN A3 A1 A3 A2 A3 A3 and A3 AN. In this way, this will be AN A1 AN A2 and this is AN AN. So these are the diagonal entries. So in this diagonal entries, all the components are same. So you write, please write here these things. A1 A1 A2 A2 A3 A3 dot dot and this is the AN AN. So extract those elements from these diagonal entries to where? So how many cells are there in this array? In this whole array, in this array, how many cells are there? N square cells are there. Okay. Out of n square cells, you picked n cells here. A1, A1, A2, A2, AN. So these cells are how many? N cells. Then how many remaining cells will be there? Of course, n square minus n cells will be there. If you remove those diagonal cells, the remaining cells will be n square minus n. So now again, form a new chart. Okay. So here, so these cells are for diagonal entries. So n cells are there, and these cells for those entries which are symmetric about the diagonal. Do you know what do you mean by symmetric about the diagonal? This, this cell, this cell, and similarly A31, A13. So you pick those ordered pairs here. So here is A1, A1, A2, A2, A3, A3, or here AN, AN, and here A1, A2, A2, A1, A3, A2, A2, A3. So you pick ordered pairs of this form. Okay, you just interchange the components. How many such cells are there? This red colored cell, how many these red colored cells are there are here? So of course n square minus n. There are 9 n square cells. You removed diagonal cells. So you remove the diagonal cells here. So n square minus n cells are remaining. Now divide by 2 because you are picking 2 at a time. So n square minus n upon 2 cells are there. Okay. Now for identity relation, what you need? A1, AN, 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 A1, AN, AN. Only one. Only one identity relation is possible because in order to have identity relation, इसके पास कितनी choices हैं? This has one choice. इसको आना ही पड़ेगा. इस ordered pair को आना ही पड़ेगा I के अंदर. इस ordered pair को आना ही पड़ेगा I के अंदर. इस ordered pair को भाई साहब को आना ही पड़ेगा I के अंदर. इनटू इस ordered pair को नहीं आना है, इसको भी नहीं आना है, एक choice. इसको भी नहीं आना, नहीं आना, एक choice. If you apply the technique of multiplication, you will see that the answer is 1. तो identity relation कितने हैं यहाँ पर? 1 है. Now moving to the reflexive relation. रिफ्लेक्सिव रिलेशन में आप ध्यान से देखना, आइडेंटिटी तो उसके अंदर आएगा ही आएगा. मतलब इसको आना ही आना है, इसको भी आना ही आना है, इसको भी आना ही आना है. यहाँ के हर एलिमेंट को 100% गारंटी के साथ आना है. तो एक ही तरीका है उसका. बट यहाँ हमारे पास चॉइस है. व्हाट आर द चॉइसेस? इस ब्लॉक को देखो, यहाँ पर एक्सप्लेन कर रहा हूँ मैं. व्हाट आर द चॉइसेस? आर अगर रिफ्लेक्सिव है, आई उसके अंदर आएगा. आ गए यहाँ से 1 1 चॉइसेस. ये एलिमेंट A1 कामा A2, A2 कामा A1, ये आ भी सकता है, नहीं भी आ सकता. ये भाई साहब आ भी सकते हैं, नहीं भी आ सकते. इनके आने ना आने से आर की सेहत पे कोई फर्क पड़ने वाला नहीं है. आर रिफ्लेक्सिव ही रहेगा. अगर आई आर के अंदर आ गया तो और बाकी कुछ आता है नहीं आता है, इट डजंट चेंज द बिहेवियर. आ जाए तो बहुत अच्छा, ना आए तो बहुत अच्छा. तो ये आ भी सकते नहीं भी आ सकते. तो हमें तो सारी पॉसिबिलिटीज काउंट करती हैं, आ भी जाए ना भी आ जाए. तो हाउ मेनी चॉइसेस आर देयर? तो इस पूरे सेल को आने के कितने तरीके हैं? ये वाला आ जाए, ये ना आए, ये वाला आ जाए, ये ना आए. So how many choices are there? Four choices. So this has four choices. Similarly, this has four choices. Everyone has four choices. And how many cells are there? N square minus n upon 2. So how many by multiplication number of relations will be? Into 4 raised to n square minus n by 2. That is 2 raised to n square minus n. And that is equal to 2 raised to summation twice of n minus 1. This is the total number of identity relations. So 2 raised to n square minus 1 is the number of identity relations. So are you getting my point? What I am saying? So number of identity relations are how much? 2 raised to n square minus n. These many identity relations are, sorry, reflexive relations are possible on the set A. Now question is irreflexive relation. Answer will be same. क्योंकि irreflexive relation में उसको ये सेल नहीं चाहिए, ये नहीं चाहिए, ये भी नहीं चाहिए वन, ये भी नहीं चाहिए वन. सिर्फ यही कंडीशन तो है, यही नहीं चाहिए. ये आ भी सकते, नहीं भी आ सकते. तो 4 चॉइसेस है हर एक सेल की. अगेन 4 रेज टू एन स्क्वायर माइनस एन, 2 रेज टू एन स्क्वायर माइनस एन. इरेफ्लेक्सिव रिलेशन हो जाएगा यहाँ से. सिमेट्रिक रिलेशन. व्हाट डू मीन बाय सिमेट्रिक रिलेशन? सिमेट्रिक रिलेशन के लिए उसने ये बोला है, अगर ए कामा बी आर को आएगा तो बी कामा ए भी आर को बिलोंग करेगा. दिस इज द ओनली रिक्वायरमेंट फॉर रिफ्लेक्सिव रिलेशन. सो देखिए, ये जो सेल है, ये भाई साहब आ भी सकते हैं, नहीं भी आ सकते. अगर आ जाएंगे तो रिक्वायरमेंट ऑटोमेटिकली फुलफिल्ड है. इफ ए वन कामा ए वन बिलोंग्स टू आर, देन कंपोनेंट इंटरचेंज करने के बाद भी आर को बिलोंग करेगा ये. तो इसके पास दो चॉइसेस हैं. इट हैज आल्सो टू चॉइसेस. सो इनके आने के टू टू चॉइसेस हैं. व्हाट अबाउट दिस? इसको थोड़ा ऑब्जर्व करते हैं. सपोज ए वन कामा ए टू आ गया और दूसरा है ए टू कामा ए वन. एक पहली चॉइस दोनों ना आए, दूसरी चॉइस पहली आ जाए दूसरा ना आए, तीसरी चॉइस पहला आ जाए दूसरा, पहला ना आए दूसरा है, और चौथी चॉइस क्या हो सकती है? दोनों आ जाए. अगर ये चॉइस है तो कोई प्रॉब्लम है क्या? अगर कोई रिलेशन में ये चीज हो रही है, ना तो ए वन का ए टू आ रहा, ना तो ए टू का ए वन आ रहा है, तो चेक करने की कोई जरूरत ही नहीं है फिर सिमेट्रिक की. बट अगर ऐसा हो जाए, दिस इज नॉट पॉसिबल. अगर पहला आएगा तो दूसरे को आना ही पड़ेगा. तो ये नहीं हो सकता और ये वाला नहीं हो सकता. हाँ, ये हो सकता है सिमेट्रिक के लिए. यहां से हर केस से आपके दो दो चॉइसेस फिर से आ गई. तो रूल क्या बन गया सिमेट्रिक रिलेशन के लिए? 2 रेज टू एन इंटू 2 रेज टू एन स्क्वायर माइनस कितना आ गया? एन. डिवाइड बाई कितना? 2. ये कितना आ जाएगा? एन स्क्वायर प्लस कितना आ जाएगा? एन आ जाएगा. और डिवाइड बाई 2 कौन लगाएगा? एंड दिस इज नथिंग बट दिस इज द समेशन ऑफ एन. इतने रिलेशंस पॉसिबल हैं यहाँ. सो आई एम रबिंग दिस. इस ये कैलकुलेशन आपको स्वयं करनी है. वंस यू डू दिस कैलकुलेशंस यू विल गेट द आइडिया. तो सिमेट्रिक रिलेशंस की जो नंबर है 2 रेज टू n square plus n by कितना 2, these many, and in symbols you can write this 2 raised to summation n. N is running from 1 to capital 1 to n. K equal n is running from 1 to n, k equal to 1 to n. This symmetric relation. asymmetric relation के लिए क्या करना होगा? asymmetric relation का मतलब है कि सिमेट्री जिसके कारण हो रही है वो चीज ना हो। मगर एक इसका मतलब ये कि अगर असिमेट्री का मतलब ये है कि इफ ए कामा बी आर को बिलोंग कर जाए तो भी किसी भी हाल में बी कामा ए आर को बिलोंग नहीं करना चाहिए। तो यहां से चेक करो, देखो ये बिलोंग कर सकता है क्या? ऑफकोर्स नहीं कर सकता है ये, क्योंकि ये अगर कर गया, और असिमेट्रिक मैंने बोला है कि आई तो आर के आता ही नहीं है, आर के अंदर आई तो है ही नहीं है असिमेट्रिक रिलेशन में, तो ये तो है ही नहीं, वी आर नॉट द मेंबर ऑफ असिमेट्रिक रिलेशन। यहाँ देख चेक करते हैं, टेक द फर्स्ट सेल ए वन कामा ए टू कामा ए वन। नाउ चेक क्या हो सकता है, क्या ऐसा हो सकता है क्या पहला आ जाए और दूसरा भी आ जाए? ऐसा नहीं हो सकता। हाँ, पहला आ जाए दूसरा ना आए, यही तो चाह रहा है वो, यही तो चाह रहा है वो, पहला ना आए दूसरा आ जाए, यही चाह रहा है वो। मतलब ऑर्डर्ड पेयर इंटरचेंज करने के बाद नहीं आना चाहिए, दोनों ना आए ये भी चलेगा, इसको भी कोई प्रॉब्लम नहीं है, तकलीफ नहीं है। तो हाउ मेनी पॉसिबिलिटीज आर देयर? गेस। अगेन सो देयर आर ओनली टू पॉसिबिलिटीज, ये दोनों चीजें हैं, ये तीनों, ये आ सकता है, इसको लेना पड़ेगा। तो अगेन वी हैव थ्री चॉइसेस, थ्री यहाँ, तो यू मल्टीप्लाई, तो व्हाट यू विल गेट 3 raised to n square minus n by 2. These many asymmetric relations are possible. Still one case remains to discuss, that is anti-symmetric relation, and how many anti-symmetric relations are possible. So I am leaving this to you to read this. So I am finishing this lecture here. Thank you very much.